Let's explore some of the interesting relationships that exist between our binomial coefficients. So our binomial theorem, everything starts with that when we're trying to play with these relationships. And I've written it in sum notation there. 1 plus x to the power of n, the sum of our general term, nckx to the k, going from k equals 0 to n. And if I was to write every term out, I'd see something like that. I just want to find the value of the sum of all the binomial coefficients. How would I do it? But notice, it's k equals 1 to n. Everything starts with the binomial theorem. This is what we want to end up with. The sum from k equals 1 to n of nck. The binomial theorem is what I have. I need to make a sensible substitution. Now, I guess the first sensible substitution, if I just want nck, it's like saying, well, how can I make that x to the power of k disappear? Not that it really disappears. Well, if I just let x equals 1, because 1 to the power of k will always be 1. So I'll be left with the sum of nck. Now on the left-hand side, I get 1 plus 1 to the power of n. But of course, that's from k equals 0 to n. But we want 1 to n. What I'll do is I'll pull out that first term when k equals 0 out of the sum, nc0. But we've also got a property that says nc0 is always equal to 1. So now I've got the result I want. Well, this sum from 1 to n will always be 2 to the power of n minus 1. That's how we can prove something like that, or find that value. What about if all I'm interested in is all the odd ones? So nc1, nc3, nc5, all the way up to whatever the last odd one is. Start with the binomial theorem. Once again, I don't have any mention of x in there. I'll do the same substitution that I did before when x equals 1. But this time, I'm actually writing the sum out because that's what they've asked me, and I want to try and get that pattern. I've got all of them. So I know all of them will add up to be 2 to the power of n. That in itself is a nice little property. Any row in Pascal's triangle will always add to be 2 to the power of n. But I don't want all of them. I want just the odd ones. So if I now do another substitution, but this time I'll make x equal negative 1. That gets us negative 1 to the power of k. It's that alternating thing that we've seen before. So now our terms alternate plus minus, plus minus, plus minus, which will allow me to cancel the odd ones or the even ones depending on which ones I'm interested in investigating. In this case, I want to be left with the odd ones. 1 minus 1, in case you hadn't worked out, is 0. So that's all equal to 0. But to do that, if I subtract the second one from the first one, then all of the even ones will now disappear, and I'll be left with 2 lots of nc1 and 2 lots of nc3 and so on and so on and so on. Divide both sides by 2 and I've got it. All the odd ones add up to be 2 to the power of n minus 1. The interesting thing is all the even ones also add up to be 2 to the power of n minus 1 as well. Ooh, k nck. There's the binomial theorem, but let's have a look at what we're trying to do. Yes, I want the x bit to go away, so it does suggest I'll do x equals 1, but that won't leave me with k times nck. How on earth could I get that k in the front of the nck? Well, that's where we use calculus, because that's what differentiation did. We got that power and it comes to the front. So if I differentiate both sides of this expression, so on the left hand side, chain rule, bring down the power, lower the power, diff the inside. On the right hand side, I now have k times nck. Substitute in the x equals 1 and I've got the pattern that we want. K times nck. The left hand side, 1 plus 1 is 2, but again, they want from 1 to n, my pattern's 0 to n, so if I extract that first term, which in this case will just be 0, because it's going to be 0 times nc0, we have the result that we're looking for. So each one of these, we just start with the binomial theorem and go, okay, how are we going to manipulate this to get what we want. That then brings up this real interesting one. They're giving us a hint on how to do it by equating the coefficients of x to the power of n on both sides, because these two expressions would be the same. 1 plus x to the power of n times 1 plus x to the power of n is the same as 1 plus x to the power of 2n. So if we equate the coefficients on both sides and compare those, we should be able to come up with this lovely result. The sum of all the binomial coefficients squared will be 2n factorial over n factorial squared. That's with the binomial theorem, which of course is this when I expand the whole thing out. Let's look at the left-hand side. I just want the coefficient of x to the power of n in 1 plus x to the power of n times itself. In other words, what I just wrote times itself. But I only want the coefficients of x to the power of n. So which ones do I pick out? Well, NC0 over here must be multiplied by the last term, NCN x to the power of n. That'll get me something x to the power of n. But then NC1 x would be times NCN minus 1 x to the n minus 1. That'll get me something x to the power of n. NC2x squared will go with the NCN minus 2 x to the n minus 2. And so on and so on. I'd keep matching them up until I'd get to the very last one, NCN x to the n, and that will be paired up with the NC0. So the coefficient of x to the power of n would be this. NC0 times NCN plus NC1 times NCN minus 1, so on and so on and so on. So how do I get to what I want? I now use one of the other properties that we know. The fact that Pascal's triangle is symmetric. Because NC0 is the same as NCN, and NC1 is the same as NCN minus 1, and so on and so on. So actually, I have all the binomial coefficients squared, which was the left-hand side of what we were trying to prove. Let's now look at the other side. This one's a lot quicker, because it's just a binomial expansion. I want the term that would have x to the power of n. So this one would be 2nc0 plus 2nc1x and so on and so on. Somewhere in the middle there would be a term 2ncn x to the power of n. And it's the only term in there that would be x to the power of n. So I know on the right hand side of the expression, that is our coefficient. Those coefficients are going to have to be the same because we said these two expressions were the same. So therefore, I now know it's equal to 2ncn. Not quite what we were trying to prove. Now we have to go back to the definition. Well, it's 2n factorial over n factorial. Be careful how you write this. It is so important that that 2n is in parentheses, because otherwise what you're saying is 2 times n factorial. No, we're not saying that. It's 2n factorial. But look at the bottom. N factorial times n factorial, that's the n factorial squared that we were trying to get. We've proven that expression. Have a look at this question from the 2020 paper. Well, look, basically that's what we just did. Part A was pretty much what we just did. Use that identity to show that. Fine, so we've done that part of the question. They then followed it up and said this. It then went back to combinatorics and turned it into a perms and cons type of question. And said, look, a club has 2n members, same number of women as it does men. So there's n women and men. A group consisting of an even number of members. So either this group has no members. Is that actually a group if you've got no one? Anyway, 2 members, 4 members, and so on. But it's always an even number of members, and there's an equal number of men and women in there. Show giving reasons that the number of ways of doing that would be 2ncn. Well, if I had to choose k men from a group of n men, there would be nck ways of doing that. But similarly, if I had to choose k women from a group of n women, there would be nck ways of doing that. So therefore, the number of ways of choosing k men from a group of n men and choosing k women from a group of n women, so I've always got the same number of men as I do women, must be nck times nck, which is nck squared. So the total ways would be the sum of all those. Because if there was none in the group, again, is that actually a group? We're saying there would be NC0 squared ways of doing it. If there were 2 in the group, we're saying there's NC1 squared ways of doing it, and so on and so on and so on. So all the different possibilities must be that. And we just proved in part A that that's the same as 2NCN. But it didn't stop there. It then said this. From the group chosen in part B, one of the men and one of the women are then selected as leaders. Show given reasons the number of ways to choose the even number of people and then choose the leaders is this. 1 squared times NC1 squared and so on. How many ways can we choose the leaders then? It would be NCK squared times K times K. We just said the total number of ways of choosing our groups was NCK squared. Okay, I said that was the same as 2NCN, but it was NCK squared. But then we're going to choose the leaders. If I've got K men, how many ways can I choose a leader? K. Only one of them is going to be the leader. Same with the women. So I multiply it by K and then multiply it by K again. So we get the sum of K squared NCK squared. K equals 0 is not possible. As if my group is 0, again, is that actually a group? But if you've got a group of 0, how could you choose a leader? You can't, there's no one there. So that's why we don't have to worry about the K equals 0 for this one. It's just K equals 1. And that is 1 squared times NC1 squared plus 2 squared NC2 squared and so on. But it didn't stop there. They then said, oh no, now we're going to reverse the process so that the leaders are chosen first. So first they choose 1 man, then they choose 1 woman. They're the 2 leaders. Now we're going to choose the groups, still having an even number of women and men. By considering this reverse process and using part B, find a simple expression for the sum in part C. So we're now going to choose the leaders first. But again, we're always going to have n possibilities. Because remember, it's a group of n people. There'll be n possibilities for the male leader and there'll be n possibilities for the female leader. And we're going to choose that first. Then we're going to choose the groups, which is like the original question, but instead of the groups that I'm choosing from being n people, I'm now choosing from n minus 1 people, or k minus 1. We're going to choose k minus 1 men from the n minus 1 men, because we've already got 1 person. So I don't need k, I only need k minus 1 to complete the group. And I'm choosing from n minus 1 because I've already chosen 1 person. There's only n minus 1 left that I'm choosing from. And we know that will be n minus 1 c k minus 1. Choosing k minus 1 from n minus 1. And we'll do the same for the women as well. So the total number of ways will be the sum of n squared times n minus 1 k minus 1 squared, and k will equal 1 to n, which will be n squared, n minus 1 c naught squared plus n squared, and so on and so on and so on, which I could factorise out, the n squared, which then equals, well, we've got an expression for this. It was written slightly different, but we found all of those squares were the same as 2NCN. But the difference in this one is instead of being 2NCN, it's 2n minus 1 c n minus 1. There's the expression they were looking for. A very interesting question that particular year. Exercise 15D.